Okay, in this video lesson, we're going to take a look at what happens to a gas as we change these different variables that we've discussed before. Okay, so first of all, if we change one thing, something else has to be affected. And as we go through this, we'll talk a lot about collisions as we do each one of these different changes. Okay, we're going to look at them one at a time. That's going to allow us to kind of like eliminate all the other variables. And eventually, we'll be able to look at these mathematically, both one at a time and as a big group. Okay, to do that, we got to go back to collisions. Now, we're also going to take a look at this simulation to kind of work our way through it. It's a FET simulation under the ideal gas law. So here's our simulation, and we're going to start off by turning on the width. This width is the way this simulation simulates volume, okay? It's only a two-dimensional simulation, so we're going to use this to kind of represent volume for us, even though it is actually a length. And then I open this window up because I want to be able to put particles in batches. I can use the bike pump if I want, but I just think it's a cleaner way of doing it. So we'll just start by adding 50 particles, maybe 100 particles in to our simulation. And when we do that, we see right away that by adding particles in, we're going to get some pressure, okay? Right now, temperature is not changing, and that's staying the same, and volume is not changing, okay? So our first scenario is how are pressure and volume related to each other, okay? So for example, if I grab this handlebar and I close the volume down, what should I expect to happen to pressure? So we're at 10. If I go from 10 to 5, okay, notice I cut my volume in half and my pressure doubled, okay? So as volume went down, pressure went up. Now if we back this off, every time I move it and give it more space, notice what happens to my pressure. So for every increase in volume, I get a proportional decrease in pressure. So as volume goes up, pressure is going down proportionally. We call that an inverse proportionality, okay? In terms of our volumes and pressures. If we were to graph this and go to the over to the iPad, we say that this is an inverse proportionality. Okay, and graphically what that means is if I start here, let's say at this pressure and this volume, if I increase my volume, my pressure has to go down and it has to continue as we work. So what ends up happening is we end up getting this inverse proportional graph or this curved line that represents that, okay? Now let's talk about why in terms of collisions, okay? So if you think about it, if the temperature doesn't change and the amount doesn't change, so we're holding their speed constant and we're holding how many particles in here constant. If I give them more space, how many collisions are going to happen? Well, with more space, there's less collisions. If I give them a very little space, there's a lot more collisions happening here. And pressure is directly related to collisions, okay? So the more space I give them, the more spread out they are, the less collisions that happen. As a result, there'll be less pressure. So it comes down to the fact that we can't speed them up or add more particles in, that volume and pressure are inversely related. Okay, we're going to erase that and we're going to kind of start over here. So I'm going to bring this down to about 10, and then I'm going to add in, I'll use the pump this time, another 100 particles. And in this case, I want to make sure my pressure does not change, okay? So I'm going to go over here under holding constant. I'm going to click and I'm going to hold pressure constant, but allow a change in volume, okay? So now I want to deal with how pressure is going to be held constant, how volume and temperature are related to each other, okay? So down here I have my toggle switch, and what I can do is I can heat up this gas. And notice what happens to my volume as I heat up the gas. It obviously increases, okay? So let's talk about why. Well, if the gases are hotter, that means that they are moving faster. If they're moving faster and we're not going to allow more collisions, we better give them more space to run, okay? Same idea. If we cool this down, they get slower and slower and slower and slower and slower and slower. But we need to make sure the collisions stay the same. So if they're moving slower, to maintain collisions, we give them less space, okay? So now warming increases. Cooling decreases. And again, we have a proportionality, but now it's a direct proportionality, okay? Or we sometimes say these are directly related to each other. So as a result, we have a direct proportionality for volume and temperature when pressure and amount is held constant. And with the direct one, if I start here, as I increase my temperature, volume will go up. If I increase more, it'll go up, it'll go up, it'll go up, it'll go up, it'll go up. So we end up getting a linear regression on this one that will force itself down through the origin. Because if there's no temperature, there has to be no volume for our gases. Okay. We continue on with this idea. Again, I'm going to kind of erase my stuff here. Yep, I understand that. Sometimes it gives me an error message. I'm going to reset my volume to 100. And now I'm going to talk about pressure versus temperature. Okay. So I'm going to make sure my volume is held constant. I can't move my volume in here. And I'm going to add in, let's just add in 100 particles, let's say. And we'll see what's going on with our pressure. So again, our pressure is about 11 to 12, someplace in that range here with these 100 particles in here. Okay. And now I've locked my volume. So now as I warm this up, those particles are going to move faster and move faster and move faster and move faster. Well, if they don't have any more space and they're moving faster because they're hotter, they have more kinetic energy, man, that's going to mean there's more collisions, right? This is the reason why we say don't run in the halls, right? Now, if I cool them down, they move slower. And as they're moving slower and slower and slower, there's less times that they're going to collide with that wall. With less collisions means less pressure, okay? Because we're not changing the space or how many particles are here. Again, we have a direct relationship. Which means as temperature increases, pressure has to increase in the same fashion. So again, we get a linear regression for our progression here, okay? Now, those are kind of our three big ones. And in those cases, none of those cases will be changing the amount. So now we're going to go on. I'm going to reset my program. And now what I'm going to do is change the amount of our stuff, okay? So I'm going to hold my volume constant in this case. And nope, sorry, that's not true. That's why I don't like using the bike pump. All right, so to start this thing off, we need to get some particles in here. So I'm just going to put in 100 particles, okay? Actually, I'm just going to put in 50 to start. And I'm going to make sure that the pressure is held constant with temperature. Now I'm going to add more particles. So let's see what happens to my temperature as I add more particles in, okay? So if I go from 50, let's go to 100. What happened to my temperature? Okay. Let's add a little bit more. Okay. Notice, this might be surprising to you, but as we put more particles in, the temperature keeps dropping, okay? So in this scenario, when we have temperature versus our amount, if we hold pressure constant and volume constant, okay, the more particles we have in here, the colder they have to be. This is because we can't have more space and we can't let them collide more, okay? So every time we add in 50 more particles, it has to cool down everything inside of here to allow them to be here without changing pressure and volume. This is an odd scenario because in real life, this is not usually what happens. In real life, when we add more particles in, we typically change the pressure inside because pressure tends to be our most common variable that gets changed. Okay, it's harder for us to control pressure. But theoretically speaking anyway, if we wanted to get more particles in here and did not want that pressure to change, the only way we could do is as we added in more particles, we also have to cool it down. Notice how every time I've done that, it's cooled it down. Okay, so what that tells me is as my number of particles increase, my temperature has to go down. So I again get an inverse relationship here. So the amount of particles is inversely related to my temperature, okay, for this one. And again, it all comes down to collisions. I can't have more collisions. I can't give them more space. So if I put more particles in there, they have to move slower So those other two things stay the same. And if they move slower, they have to get left at less temperature. Okay? Let's reset our stuff here again. And now we're going to talk about amount versus volume. Okay, so in this case, I'm going to put in, let's say, 100 particles. And I'm going to hold my volume constant while allowing, I'm going to hold my pressure constant. I'm not going to change my temperature. So now as I move my particles, the only thing that should change is my volume, okay? So I'm not going to add in a lot of particles. So I'm at 10 meters. I'm just going to add in, let's say, one more particle. Okay? Notice how it went up a little bit. Added another particle, another particle, another particle. Every time I add in a particle, it's going to increase my volume. Again, let's talk about why, okay? So as we have more particles, if we're not allowing more collisions and we're not allowing it to cool down or warm up, we have to give it more space. More particles need more space to maintain pressure and maintain temperature. Okay? So in this case, as I add more particles, my volume has to go up also. So as a result, I get another linear regression. So that is a direct relationship. Or I should call it direct proportionality. Okay? In this case. Again, always bringing it back to collisions. Why is this happening? Well, pressure can't change. That's a rule we've set up. So collisions have to stay the same. Okay? We're not allowing temperature to change either. So to keep our collisions the same, every time I put another particle in here, I had to give it that proportional space to move around to not increase my collisions. So it's all proportional to how much space they need to maintain those collisions. We'll reset this again. And now we're going to talk about the amount and the pressure. Okay, so we're going to keep our volume and our temperature constant and see what happens to pressure. Okay, so let's start off by just adding in one particle. Okay, not a lot of pressure. Add in 2, still not much. 3, 4. We start to see some pressure developing. This one probably is one of the more easy ones to kind of visualize because every time you put another particle in, if we're not changing the temperature or the space, there's going to be more collisions, right? There's more particles, more collisions. Okay, think about like a crowded subway or a crowded hallway in class, right? When you walk down the hallways between classes, you don't bump into anybody. But when you walk down the hallways between classes, or that's right, when you walk down the hallways during a class, you don't bump into anybody. You walk down the same hallway between classes, it's very likely you might bump into somebody because there's just so many more particles there, so many more people there. Okay, dump 50 in and our pressure goes up. Dump another 50 in, our pressure goes up. Dump another 50 in, our pressure goes up. Okay? So again, holding temperature and volume constant, as we put more particles in, that will create more collisions. More collisions means more pressure. Okay? So again, we graph this, and as my amount keeps going up, the pressure will go up proportionally to that, and we're going to see another linear regression. So again, we have a direct proportionality. All right. Now, that is all 6 possible scenarios that we have, okay? And from these scenarios, from these relationships, we can build equations from that, okay? So from this video, what we want to make sure that we understand is what happens when we change one thing to one other variable, holding the 2 other variables constant, okay? The beauty is when we start to bring them all together, there's no new math or no new relationship that we need to worry about. Okay, they're all kind of like independent, but have the same weight in terms of how they affect each other. So later on, if we change both temperature and pressure, there's nothing new besides the relationship, how it affects volume and amount. If that kind of makes sense to you. All right, thank you guys. That's it.